Welcome back, everyone. So this is going to be a lesson for linear algebra about the matrix of a linear transformation. And if you watched our last video, the last video was a pretty important one. It was kind of a longer video. That was an introduction to linear transformations. And this one is going to pick up right where we left off. In the last minute or so of that video, I was giving you something to kind of think about, and we're going to pick up right with that. So let's go ahead and get started. All right, so the matrix of a linear transformation, what is this all about? I want to remind you that in our previous lesson, the video before this one, we said that a transformation from Rn to Rm defined by t of x equals ax is a linear transformation. And in particular, what I mean by this is for any matrix A. As long as the matrix A is the correct corresponding size for Rn and Rm, but as long as A is the right size, you always get, to call this Rn and call this Rm. You get a linear transformation. It is not just a transformation, it is a linear transformation, and we talked about what that means last time. And in fact, every linear transformation meaning any t from Rn to Rm, can be written this way. So this is kind of the answer to the kind of question that I was asking at the end of our lesson last time. At the end of the lesson, I was asking you to think about, all right, every matrix has a corresponding linear transformation. Does every linear transformation have a corresponding matrix? And the answer is yes. And it's kind of given away, it's kind of spoiled for you in the title of this section, the matrix of a linear transformation. So yes, linear transformation is going to have a corresponding matrix A. We're going to state this as a theorem. It's going to be kind of an important theorem. But before we say it, I just have a quick definition that we need to get out of the way first, because I don't think we've said this definition yet. We've talked a little bit about matrices, but I don't know if we've said this definition. The n by n identity matrix. I subscript n, or just I. I'm going to underline identity matrix. That's what this is a definition of. Is the n by n matrix with ones along its main diagonal and zeros elsewhere. Some examples of the identity matrix is that I2 looks like this, I3 looks like this, maybe I3 is a good example, because you can see this is what I mean when I say that there are ones along the main diagonal and zeros everywhere else. The main diagonal is considered from the upper left to the lower right, And because we said this is an n by n matrix, you know that it's a square. So you can go all the way from the upper left to the lower right. I'll do one more. The identity matrix is sort of one of the fundamental matrices that is useful in linear algebra. I'll just say etc. Yeah, you can see that the larger it gets, it's just mostly zeros, except for I guess it has n entries that are ones, and everything else are going to be zeros. Now, I said that this is I subscript n, so I did I2, I3, I4, but I also said in parentheses, or just I. So sometimes we will just refer to it as the identity matrix I, and the size will be clear from context. Like if we're doing a problem where everything that we're doing in the problem is 2 by 2, and then I say something about the identity matrix, it's probably safe to assume that we're talking about the 2 by 2 identity matrix. So we can just say I if it's clear what the size is from the problem that we're working on. Okay? So we needed to get that definition out of the way, and now we can get back to the main topic at hand, which is linear transformations and their corresponding matrices. And this is going to be called Theorem 10. Theorem 10. It says, let T from Rn to Rm be a linear transformation. We're not making any assumptions on how the linear transformation is given. Is it given in the form of a matrix? Is it given in the form of a formula or something else maybe? All we know is we have a linear transformation T. Then there exists a unique matrix A such that T of x equals ax for all vectors x in Rn. And there's more to this theorem. There's going to be a little more, but I'll just give you a chance to see that. When we say there's a unique matrix A, we mean we already said let T be a linear transformation, right? So the first sentence establishes that there's a T. When we say then there exists a unique matrix A, we mean that there's a unique matrix A for this T. Like this T has a unique matrix A. Okay, I said there was going to be more. Specifically, wouldn't it be nice if we actually could find the matrix? Well, that's what the rest of this theorem is about. First it says that there exists a matrix. It also says that it's unique. And now it's going to tell us, how do we find that matrix? A is the m by n matrix. A equals. We could write a matrix in different ways. Remember that we have sometimes shown matrices by listing like column vectors? That's what I'm going to do here. T of E1 dot 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 all the way up to T of En. I need to tell you what some of those things mean. Where EJ is the jth column of the identity matrix In. That is the entire theorem. It tells us that every linear transformation, there exists a corresponding matrix such that the linear transformation can be just done as a matrix times a vector. It tells us that that matrix is unique and that that matrix can be found by applying the transformation to columns of the identity matrix. Key idea. We can find A based on how T maps columns of I. So whatever T does to the columns of the identity matrix, that kind of informs us about how T acts in general. So that tells us how to find A. So this is a powerful theorem, and we will prove this theorem today. In this lesson, we're going to prove this. But first, I think I'd like to do some little examples to help us get some understanding of it. So we'll do probably 2 examples, and then we'll do the proof. So this first one, I'll do this one. We'll do this one for us. So in our previous lesson, the one right before this, we had one of the examples that we looked at was a transformation from R2 to R2 defined by T of x1, x2 equals x2, x1. All right, so in that previous lesson, we used this as an example of a transformation, and we showed that this was linear. We went through the steps of proving that this was a linear transformation. Okay, now I haven't asked any questions yet. Now, we are going to find A so that T of x equals AX for all x in R2. This transformation is given to us not in this form. It's not given in the form A times x. It's given more as a formula, right? T of this vector equals this vector. It's telling us to take the positions and swap them. You know, x1 and x2 swap places. But I'd like us to find a matrix so that this linear transformation can be written as a matrix times a vector. All right, so we're going to use Theorem 10 to do this. Because we're going from R2 to R2, the identity matrix that we're working with is the 2 by 2 identity matrix. And the first column of it is going to be called E1, and the second column is going to be called E2. Those are vectors, column vectors. Let's just write them off to the side just to, this is the first time we're doing this, so let's just be extra clear. E1 is this, and E2 is this. And maybe for future problems, we won't even need to write the identity matrix. We'll just be able to say, all right, I know that this is what E1 is and this is what E2 is. Maybe for some other problems, there might be an E3. Okay, so the theorem says that A is equal to, I'll just show you real quick. A is equal to this. So all we need to do is find T applied to E1 and T applied to E2 and put them together. Let's find T applied to E1. We can use the transformation as given, in the form that it's given. It says to take x1 and x2 and swap them. So we get this. That's the output. Let's do T of E2. It says to take T of this the second column of the identity matrix. And when we apply the rule that's given for this transformation, we get 1, 0. By theorem 10, A is equal to T of E1, T of E2. That's it for this problem. I mean, it's a 2 by 2 problem. So we take the two column vectors that we found and just put them side by side. So the first one we found was 0, 1. And the second column vector that we found was 1, 0. And that's the answer. We found the matrix A. So that means that this linear transformation, there are two ways of thinking of it. You could think of it by the formula that was given, in which it specifically tells you what to do with each entry of the vector. You give it x1, x2, it tells you what to do with it. Or you could think of this linear transformation as being a matrix times a vector, where this is the matrix A. So you do this times any column vector with two entries, and it will have that same result. It'll have the effect of swapping x1 and x2. So it's a different perspective, a different way of thinking of this linear transformation. The fact that every linear transformation has a corresponding matrix and vice versa is pretty cool, because it means that, you know, maybe at some point we have a problem about linear transformations and we can think of it as a problem about a matrix. Or maybe sometime we have a problem about a matrix and we can think of it as a problem about a linear transformation. But I'm getting ahead of myself. Let's do one more of these kinds of problems. So I'm going to ask you to do this one, but let me write the whole thing first. So again, I'm going to revisit one of the transformations that we had in the previous video. It was from R3 to R2, and it was defined by... Now, keep in mind that Theorem 10 is only for linear transformations. You know, in the previous lesson, we had some transformations that were not linear. Well, this one was linear. We showed that this was a linear transformation in that video. And now I'm going to ask you to find A so that T of x equals AX for all inputs x, and the inputs, I guess, would have to come from R3. So why don't you pause the video and take a minute and try this. Okay, let's talk about it. So let's think about what sized identity matrix do we need for this one. The inputs are coming from R3, so we actually need to work with the 3 by 3 identity matrix here. Whether you write the identity matrix or not is up to you, but we're going to need these three columns: E1, E2, E3. And we need to see, what does T do to each of these? So T of this. Here, you know what? I'm going to set this up before I actually answer them. I'm just going to set up all three of them. Sometimes you could do this if you want. Be like T of that, and T of that. And that's going to get us... It's going to get us everything we need. E1, E2, E3. Okay, we can just do these in our head, right? So x1, x2, x3. So we get 1, 0 for the first one. We get 0, 1 for the second one, applying this rule that was given. And we get 0, 1 for the last one. So the matrix A equals, take the three results you got and put them side by side to make one matrix. And this matrix is a rectangle in this case. They have to be in that order. The columns have to be in that order. This is the only, it's a unique matrix, right? The theorem says the matrix is unique, so this is the only possible answer. Cool, so that's how this theorem works. That's how we find the matrix. You just take the transformation, apply it to each column of the identity. It makes sense that this answer is rectangular because this transformation was mapping from R3 to R2. So if we're going from R3 to R2, we can't really have a square matrix that does that. I mean, look at this, right? It goes from a 3 vector to a 2 vector. All right, so I told you that we were going to do a couple of examples, and then we were going to prove Theorem 10. So that's what's next on the agenda. Let's get a fresh sheet of paper and let's prove Theorem 10. Proof of Theorem 10. We don't prove every result in this class, but we want to prove the important ones. Okay, let T from Rn to Rm be a linear transformation. And let X be a vector from Rn. So what I just did here, the theorem says that you have a general linear transformation, but it also, in the second sentence of the theorem, it says for all X in Rn. So I just went ahead and took a general X from Rn. So we have our general T, our general X. We want to show there exists A such that T of X equals AX, and that A is unique. That's two things, right? I'm going to underline exists and unique. This sentence, this entire second sentence that I wrote, is it really a part of the proof? I mean, that second sentence isn't really proving anything. It's not really getting us any closer to proving. And you should know that when you're writing proofs, that different people have different styles of writing. And I sometimes like to write a sentence like that to sort of guide the reader and explain what we're about to do. So I think that sentence is nice, but technically you could leave it out and it would be fine. There are a lot of things in math where you want to prove that something exists and that it's unique. And, existence and uniqueness proofs show up in other courses also. Anyway, here's what we're going to do. We're going to let A be this matrix where EJ denotes the jth column of I. I'll say IN just to be clear. Now, I think that it's safe to say that this matrix that I just wrote does exist. That doesn't necessarily prove that it has the desired property. such that t of x equals ax, right? This is a matrix. It exists, but does it have the such that t of x equals ax? So let's work on that. Let's work on that. So we have, let's do t of x. We want to show that this equals ax. We can't just say it equals ax by theorem 10. I mean, we're trying to prove theorem 10. So this proof uses kind of a clever trick. A clever trick where the identity matrix times the vector x. I guess I don't know if we've really said this in this class or not. Maybe, I guess I'm saying it now. But x is equal to the identity times x. That's kind of why it's called the identity. It's a multiplicative identity. Yeah, any vector x is equal to the identity times x. It's sort of like the equivalent of multiplying a number by 1. We multiplied a vector by I. It doesn't actually change it. You can check that. You could do like a 3 by 3 example or something, and you could check that when you multiply and do the matrix vector multiplication, which we've done, you get the same result. All right, so what I'm going to do then, instead of writing in, I'm going to write it as a list of its columns. Okay, so I just took I and rewrote it as sort of the column notation. Now, if we were to do this, each column times each entry of x, that's how we do a matrix times a vector, right? We do each column times, first column of this times first entry of this, second column of this times second entry of this, and so on. So this is going to be t of x1 e1 plus ... We're not making any assumptions on how big this might be. N might be 10 for all we know. It could be larger for all we know. However big this is, we just wrote all of them. All right, so there is something important that we haven't used yet. The fact that t is linear. Because t is linear, we can pull out x1. In fact, because t is linear, we can split this up into x1 t of e1 plus x2 t of e2, etc., all the way up to xn t of en. And I'm going to say because t is linear. This is a vector equation, right? Now, we've said that an equation like this can be rewritten as a matrix equation. So here's what I'm going to do. I am going to rewrite this. Let's leave ourselves a little bit of space because the vectors might be tall. We're going to rewrite this as t of e1 ... t of en, close that. So that's a matrix, and this is a vector, x1, xn. Just to be clear about the sizes of everything, let's see. How big is this? This right here. This is a matrix, right? And it has n columns. You can see that there's 1, 2, 3, up to n. So it has n columns. So if I were to talk about the size of this, it's something by n. And how many rows does it have? Well, T maps from Rn to Rm, so there are m rows. Every time you put something in T, you get m rows. And then what's the size of this? This is n by 1. It's a vector, so it's something by 1, and you can see that it has n entries. This matrix times vector multiplication exists. It's fine. All the sizes match up. And this, in fact, equals, we said that A was this matrix. Look what we have here. This is A. This is X. So this equals AX, which is what we wanted. Period. Okay, so what did we do here? We said let A be this matrix, and then we showed that that matrix has the desired property. It has T of X equals AX. And the way that we did that, sort of the key step, was using the fact that T is linear to take this and break it up. I think that that was important. And that's why Theorem 10 only applies to linear transformations. We're not done with the proof, though, are we? We proved, here, we want to show there exists A such that T of X equals AX. We did that part. We still need to show that A is unique. Okay, so we want to show that A is unique. Let's see. Should we do that now, or should I leave that for you? Maybe I should leave that for you as an exercise. How about this? If I were continuing to write this proof, I might say something like, next, we want to show A is unique. So the textbook that I'm following along with actually leaves this part as an exercise, and I think it's number 33 in the textbook. I think I am going to leave this and say, try to finish. Try to finish on your own. You could always ask me about it later, but yeah, the book that I'm following along with uses, leaves this as an exercise, so I'm going to leave that as an exercise, proving that the matrix is unique. So we are going to say that we have proved Theorem 10. I'm going to put a little shaded in square here to indicate the end of the proof. You fill in the gaps, ... Therefore, A is unique, end of proof. And I'm going to tell you now that we've finished that, is note, A is called the standard matrix for T. So if you hear that phrase, standard matrix, that's what we're talking about. It's the matrix that corresponds to the linear transformation so that T of X equals AX. Now, it turns out that this matrix A can be used for other things besides just evaluating the linear transformation, besides just, what is T of X? And we need some definitions. Let's just get a fresh sheet of paper. We need some definitions. Now, these definitions, these words might sound familiar to you from other classes, but we're going to talk about them in the context of transformations. So I'm going to say a mapping T from Rn to Rm is called number one, onto. It is called onto if each B in Rm is the image of at least one X in Rn. So every vector in the codomain is the image of at least one vector in the domain. That's what it means to be onto. It's like everything in the codomain is mapped to. Everything in the codomain is the image of something. And the other definition is one-to-one. All right, T is called one-to-one if each B in Rm is the image of at most one X in Rn. Okay, now in previous classes, you've probably seen these terms just in regard to functions on real numbers, like, you know, a function from the reals to the reals. And you might have seen a definition for onto and one-to-one, and you might have seen a slightly different definition for one-to-one. But if you really think about it, it is equivalent to what we're doing here. We're phrasing it differently, but yeah, we're saying that each, I guess this B should have a little vector symbol above it. Each vector B from Rm is the image of at most one. So each output is the image of at most one input. That's what it means to be one-to-one. I have a couple of remarks to say about these remarks. First of all, T can be one of these, both, or neither. Okay? So there's nothing that says that it has to be one or the other. It could be neither. Off to the side, here's a couple of terms for you. Here, terms. I'm mostly going to refer to these as onto and one-to-one, but I'll just say terms. Onto can be called surjective. One-to-one can be called injective. And both, do you remember the word for both? I would ask you, if we were in class, you know, I would ask you to fill in some of these blanks. Surjective, injective. This is a bijection. Easy to remember because it says bi because it's both one-to-one and onto. Bijection. And, you know, you could say that if something is onto, you could call it a surjection, and if it's one-to-one, you could call it an injection, but usually it's the adjectives surjective and injective that are used, I guess. Anyway, so I have some other remarks. If T is onto, then the range equals the codomain. This is kind of something that it sort of feels like we want this to happen. You know, when we say that we map from Rn to Rm, and we say Rn is the domain, so we send things from the domain to the codomain, technically. But if it's onto, then the codomain is also known as the range. All right, so that's a remark. Another one, T is one-to-one if for each B in Rm, T of x equals B has either a unique solution or none at all. That makes sense with the definition, right? This remark that I just made, this follows from the definition. I don't think this needs to be a theorem or anything. It just follows quickly from the definition. You know, we're saying that the definition says it's the image of at most one thing. Well, if it's the image of at most one thing, then there's either one solution or none. That's what it means to say there's at most one. 1 or 0. So let's go on to theorem 11. Theorem 11, we're also going to prove this one. Let T from Rn to Rm be a linear transformation. All right, so right now we know that everything from theorem 10 applies, in case we need to use that. Then T is 1-to-1 if and only if T of x equals the 0 vector has only the trivial solution. Before we prove this, let's take a minute to really read it and think about it. All right, so first of all, T of x equals 0, only having the trivial solution means that the vector x would be the 0 vector, right? Let's get started. This is a if and only if. This is an only if and only if proof, so we need to go in both directions. I'm going to go in the forward direction first and say, suppose T is 1-to-1. Sometimes actually getting started on a proof can help shed some light on how the theorem works and why the theorem works, and it can actually give us a deeper understanding about the theorem. So suppose T is 1-to-1. What are we trying to show here? It's 1-to-1. We're trying to show that T of x equals 0 has only the trivial solution. Well, by definition of 1-to-1, which we just wrote a minute ago, T of x equals 0 has, at most, one solution, right? That was in the definition of 1-to-1. Then, since T is linear, the fact that T is linear seems like it's going to be important. Whenever we have a theorem about linear transformations, we can use everything we know about linear transformations. We know that T of the 0 vector equals the 0 vector. That was one of the properties of linear transformations. Every linear transformation has this property. It sends 0 to 0. Well, by definition, there's at most one solution, and 0 is a solution. So T of x equals 0 has only the trivial solution. Makes sense, right? So we used a combination of the definition of 1-to-1 and this property of T being linear. There can be at most one solution. There is this solution. Therefore, it's the only one. Let's prove the other direction. Let's prove the other direction. So other direction means that we are going to suppose that T of x equals 0 has only the trivial solution. Now, it's an if and only if proof, so we're starting from this direction and we're moving in the other direction, but we can still use the fact that t is linear. Like, t being linear is a separate sentence of its own. It's not a part of this biconditional. Okay, so we could still use the fact that it's linear. So how do you think we can do this? Suppose it only has the trivial solution. What do we want to show? We want to show that t is 1 to 1. What I'm going to do is I'm going to say, suppose t is not 1 to 1. Think about what you know about proof writing. What does this sentence mean? What is this indicating that we're going to do, right? This indicates that we're going to find a contradiction. We're doing proof by contradiction for this direction. Suppose it's not 1 to 1, we get to some kind of contradiction, therefore it must be 1 to 1. I'd like you to try on your own to come up with the next line. I've been kind of going through this. Take a minute and think about it. See if you can come up with the next sentence. I'm going to show you the first word. Then. That's a powerful word, then. Okay. So, suppose t is not 1 to 1, then what can we conclude? We could refer back to the definition of 1 to 1 if we need to. And what would it mean to not be 1 to 1? Then there is a b in Rm that is the image of at least two different vectors in Rn. So I basically took the negation of the definition of 1 to 1. If it's not 1 to 1, then we can say this for sure. Now, if we're going to aim for a contradiction, you know, there's at least two different vectors in Rn. I think it's going to help us if we give them a name. You know, instead of just saying, oh, the two vectors, like the first one and the second one. No, let's give them names. And I am going to say that they are u and v. You could call them something else if you want, but I think it's going to help if you call them something. Give them names. Give them labels. All right, I'll continue. It's not really clear what the contradiction is yet. How about this? How about this? We have t of u minus v equals t of u minus t of v. You don't have to write this little thing I'm about to put on the side, but I'm going to say because t is linear, that's what allows me to do that. What is t of u? What is t of u? Well, look at the previous sentence. We said that t of u is b. What is t of v? T of v is also b by the previous sentence. A vector minus itself gets us the zero vector. Period. However, u minus v does not equal the 0 vector. How do I know that u minus v does not equal the 0 vector? It's because u and v are different. We said that they are two different vectors. So if I take their difference, I don't get the 0 vector. So t of x equals 0 has a non-trivial solution. We just found it. U minus v. U minus v is non-zero, and t of u minus v is 0. So u minus v is the non-trivial solution to this equation. Which is a contradiction. Why is this a contradiction? Why is this a contradiction? Because look at our first sentence. We said, suppose this has only the trivial solution, and then we found a non-trivial solution. So therefore, t must be 1-to-1. Whew, all right. That was kind of a cool proof. I like that. Proof by contradiction is fun sometimes. Sometimes you don't even know what the contradiction is going to be at first, and you have to kind of explore a little bit and, go one step at a time and see where it leads you. I think that this step, going to check to see what is t of u minus v, that's kind of the big, bold step that would be hard to come up with. But once you see it, everything just kind of clicks into place. So that's the end of this proof, theorem 11. And I think that proving it does help us get a deeper understanding of what the theorem is all about. So you have a linear transformation. It's 1-to-1 if and only if t of x equals 0 has only the trivial solution. So that theorem could be used to check to see if whether or not a linear transformation is 1-to-1. Theorem 12 is also something that can help us check to see whether or not a linear transformation is 1-to-1. It's also going to involve checking whether or not something is onto. So theorem 12, let t from Rn to Rm be a linear transformation with standard matrix A. We know that that matrix exists. We know what that means. Then, this theorem is going to have two parts. Part A, t is onto if and only if the columns of A span Rm. Okay. So we're bringing in some concepts from a previous section. We talked about what it means for a set of vectors to span a space. For these vectors to span the space Rm. So if you know that the columns span Rm, then you know that t is onto, and vice versa, because this is an if and only if. Part B. Oh, and by the way, this is cool because this is telling us a way to check to see if t is onto based on looking at its matrix. Okay, so we're taking the question of whether or not the transformation is onto, and we're turning it into a question about the columns of its matrix. And a lot of linear algebra questions can just be turned into questions about a matrix. T is 1-to-1 if and only if the columns of A are linearly independent. Look at that. All right, another definition from a previous section, another phrase coming up, linear independence. Do you remember what it means for a set of vectors to be linearly independent? Columns of A could be thought of as just a set of columns, set of vectors. You check to see if they're linearly independent. It tells you whether or not T is 1 to 1. So again, we want to know if T is 1 to 1, and we turn it into a question about its matrix. So this is very practical, because this whole theorem is very practical, because it uses skills that we already know from previous lessons to check for these properties. And I think that we're going to use this theorem often. It's a very practical theorem. I've decided that we're not going to prove this one right now. I think, if I'm not mistaken, I think that we proved together, we proved theorems 8, 9, 10, and 11. So for the sake of time, I'm going to skip the proof of theorem 12, but it is in the textbook if you'd like to look at it. I try to cover the proofs of important theorems, but I also try to focus on the proofs that I feel are the most informative. Okay, so I want to show you an example problem. I said we're going to use this theorem. It's practical. Let's use it. And I'm going to write a question and have you try it, actually. It's going to have 3 parts. So wait till I write all 3. Part A, find the matrix A that describes the linear transformation. Okay, wait until I write all 3 parts of the question before you start. But I just want to say that this first part of the question already kind of packs in a lot. So find the matrix A that describes the linear transformation T of xy equals, that's 2x plus y and 3y. Sometimes my y's look like 4s, so I just try to make it clear that these are y's. 2x plus y and 3y. This first part kind of packs in a lot because it tells you that it is a linear transformation. So you don't have to question whether or not it's linear. It's telling you that it is. Part B is T onto, and part C is T 1 to 1. And I hope that part A will help you answer part B and C. So why don't you pause and take a couple of minutes and see what you can do for this one. All right, let's get started. So part A. Part A wants us to find the matrix. We did that sort of thing earlier today. So this transformation goes from R2 to R. Wait, that's not right. R2 to R2. Hold on a second. Yeah, we have two entries here, 2 entries here. Sorry, I had it wrong in my notes I was looking at. This is correct. T goes from R2 to R2. So we need to use the identity matrix that's 2 by 2. Okay? We just need to know which identity matrix to use. So you check T of the first column of the identity. We're going to see what we get. We're going to do T of the second column of the identity and see what we get. And you have to do these manually. You have to refer to whatever is given. So X, Y. So you can do these sort of things with steps if you want. Like this is 2 times 1 plus 0 over 3 times 0. And this simplifies to 2, 0. This one over here is 2 times 0 plus 1 and 3 times 1. So it equals 1, 3. Put these together and you get the matrix 2, 0 as the first column, 1, 3 as the second column. So that's the answer to part A. Now the new part is part B and C, trying to use theorem 12 maybe, unless you see some other way to do it. Okay, is T onto? And theorem 12 says T is onto if and only if the columns of A span Rm. So do you think the columns of this matrix span R2? All right, so to use theorem 12, this is kind of scratch work right now. To use theorem 12, do the columns of A span R2? Because that will give us our answer. Recall. Theorem 4. We're going way back. Theorem 4 from, well, in the textbook, it's in section 1.4. Say the columns of A span Rm if and only if A has a pivot in every row. See, those old theorems are turning out to be useful. We could look at this matrix and figure out, does it have a pivot in every row? If it does, then the columns of A span R2. And if the columns of A span R2, then by theorem 12, then it's onto. So I am going to say, yes, A has a pivot. So this stuff up here was kind of scratch work, a little bit messy, but I'm going to just explain this or summarize. A has a pivot in every row. I think we can see that by observation. So the columns of A span Rm by theorem 4. So yes, this linear transformation is onto. And we found out by looking at its matrix A. Next part is T 1-to-1, and I'd like to use theorem 12. So to use theorem 12, are the columns of A linearly independent? And you might have to think back to the lesson that we had on linear independence. When linear independence was first introduced, we had a bunch of different facts and theorems about linear independence for you know, sets of 2 vectors, sets of 3 vectors, and so on. And look at these two things as vectors, right? We're thinking of this set, and we're asking ourselves, is this set a linearly independent set? Do you remember any facts that we may have talked about that could tell us? That we could actually use the definition of linear independence and like manually try to figure it out, but there were some shortcuts also. All right, I'll get to the point here. I'm going to say yes from a fact in section 1.7 in the textbook. I don't think this fact had a name. Like, I don't think this was a theorem. So it was a fact from our lesson on linear independence, and it says that this set is linearly independent because neither vector is a multiple of the other. Remember that? When you have a set of only 2 vectors, you can tell if it's a linearly independent set by whether or not a vector is a multiple of the other. That's for when there's only 2 of them. So pretty cool. In this problem, in part A, we found the matrix corresponding to this linear transformation. The linear transformation was not originally given to us in that matrix form, T of x equals ax. So we found the matrix ourselves, and then we used Theorem 12, which we just talked about, but we also used some older facts as stepping stones to get us where we needed to go. And we found that, yes, this transformation is onto, and yes, it's one-to-one. So in fact, we could say that this is a bijection. It's a linear transformation that is a bijection. So we're going to wrap things up in a moment, but I'll give you a chance in case you're still writing any of that. All right, so I know that was a lot to take in. We were kind of pulling from some older theorems and some older facts, and it can be tough to kind of see the relevance of older things, but we need to keep those things in mind. So if you're following along with the textbook like I am, then this is the end of chapter 1. And that means that in the next lesson, we're going to kind of shift to a little bit of a different topic. So now's a good time to go back and sort of review everything and review, you know, the lessons so far that kind of constitute chapter 1. So I'll say that's it for now, and I hope everybody is doing well, and I'll see you soon. Bye.